In this brief video, we're going to explain all the topics in this semester, starting from the first stage and ending in the fourth stage. We hope we can talk about all the topics we saw, and we hope you like it. Stage number 1: Physics Foundation. Physics classification and background. We have two types of physics: classical physics and modern physics. Classical physics studies motion, light, sound, heat, and electromagnetics. Some of the most important characters were Newton, Pascal, and Galileo, and it took place in the 19th century. The modern physics studies microscopic world, and the important characters of modern physics were Hawking, Einstein, and Bohr. It took place in the 20th centuries until now. Physics in general studies matter and its motion and behavior through space and time, along related concepts such as energy and force. We have several branches in classical physics. First, mechanics studies motion, like tachometer, turbine, and GPS. Acoustics studies sound, like ultrasound, solder, sonar, and loudspeaker. The thermoelectrics studies heat and temperatures, like steam boiler and chiller. Here, electromagnetism, like dynamo, multimeter, compass, and no brakes. Optics, microscope and telescope. Now, in modern physics, solid state physics studies of reheat matter or solids, and X-ray crystallography. Another type of modern physics is the elementary particles of physics. It studies particles whose substructure is unknown. Other one is relativity. Describes the relationship between space-time and matter, like black holes. Atomic physics is related to atom structure evolution, like alpha, beta, and gamma. Nuclear physics studies atomic, nuclear, and their constituents and interactions. Magnetic resonance imaging, quantum mechanics studies objects that have wave particles, duality, and photons. Quantum mechanics lasers. And all of this is modern physics. Here we have Newton, representing classical physics. Is usually concerned with everyday conditions like speeds much lower than the speed of light and sizes much greater than the one of atoms. All knowledge is obtained through experiments, and matter has cause and effect relationship. Here we have Einstein, representing the modern physics. The microscopic particles do not follow motion laws. The matter has wave particles laws. Is usually concerned with high velocities and small distances. Also, we saw conversions like inches, we have centimeters, days to hours, hours to minutes, minutes to seconds, miles to kilometers, feet to meters, slug to kilograms, seconds to minutes, and we saw conversions. I repeat, and we saw the three main unit systems. We also saw physical quantities. The fundamental quantities are the units that are selected arbitrarily and are not defined in function of other physical magnitudes. By other side, the derived quantities are formed for two or more fundamental units. These ones make these ones. We have some physical quantities right here: acceleration, mass, area, length, temperature, force, density, energy, and speed. The unit of acceleration is meter per second to square. The abbreviation is this one. and the fundamental is derived. The physical quantity is mass, unit kilogram. Here is the abbreviation, and here is that is a fundamental. Here is his fundamental. Area, square meter. Square meter, derived. Length, centimeter, cm, fundamental. In this way, we have the most common multipliers and prefixes for metric units. We have the prefix tera, giga, mega, and kilo. We have all the abbreviations, the values. We have other prefixes like deci, centi, milli, micro, and nano. We have abbreviation like there are like symbols or letters, and the values of each one. We have here some problems, and here we have that there are three main unit systems. We have the SI, the International System of Units, and we have the CGS, established in 1832 by Carl Gauss to base system of absolute units on the three fundamental units of health, mass, and time, like centimeters, gram, and seconds. Here we have the British one. It's called FPS for foot-pound second. The system developed historically and not very scientifically. However, is widely used on consumer products and industrial manufacturing. In English, we know it as USCS. Here we saw some equivalents, as I told you, and that's it. These topics are from stage number 1, and let's go with stage number 2.
So let's talk about the triangle method. First, you select a reference axle and a first vector and draw it in a scale using the correct direction. Draw a second vector in a scale using the appropriate direction and place its origin on the first one's point. As we can see here, this is the first one, and it says that you put the second one in its finish point. So here it is, the finish point, and this is where the second one starts. To find the sum of resultant, draw a straight line from the origin of the first vector, which is this one, to the second one's point, which is here. The scale length of this line is the resultant magnitude. So in this case, this line would be the resultant. A parallelogram method. So first you select a reference axle and a first vector and draw it in a scale using the correct direction. Draw a second vector in a scale using the appropriate direction and it starts in the origin of the first vector. To find the resultant, draw a straight line from the origin of the two vectors to the intersection of parallel lines. So the resultant here would be this C line because it interrupts the parallel direction. And last but not least, we have the polygon method. It's called like this because the addition of vector process creates a closed polygon figure. Of course, the polygon which has fewer sides is a triangle that emerges when two vectors are added or subtracted. So this is more likely to be like a triangle method, but a triangle that will emerge when two vectors are added or subtracted. So if you have the triangle method, which is this one, but you add two more vectors, then you will have a polygon vector. So that would be it for stage 2. Thanks.
Okay, at this stage we saw the kinetics motion in one dimension, like when an object is moving in one dimension in a straight line. We saw things like falling objects or gravitational acceleration, like all the concepts with this thing, like um, acceleration, the velocity, the speed, the average speed, the AULM, the something like that, all other things. Let's go to the topics. We saw the mechanical motion, we saw to the mechanics, something like Aristotle, the mechanics and motion. We saw to the dynamics, the kinetics. We saw the particle model, the translation model. We saw to the trajectory, the path, the road of the trajectory. We saw to distance and displacement. We saw the displacement, the distance. We saw the speed and velocity, how they are seeing. We saw okay, all these formulae, the formulas. We saw the average speed and average velocity. We we saw to acceleration. Did a lot of exercise about the acceleration. We saw the motion in one dimension, that is the moment in one dimension, okay, like in a planar vector, like that. We saw to some interpretation. We saw the linear motion equations. There are the XO, initial position, the final position, the initial velocity, the final velocity, the acceleration, and the lapsed interval of time during the change of position. We saw to the interpretation of the results, a lot of things that we saw. We saw the graphics analysis of motion in one dimension, like position versus time, velocity versus time, acceleration versus time. We saw the position versus time, some graphs like this one, the time in seconds. We saw to the velocity. We saw the position, the velocity, and acceleration. We saw a lot of graphs, how you were looking there. More graphs, how you can look there. We saw that's one of my favorite topics, the free fall. We saw to the gravitational acceleration, but my favorite topic is free fall. That's the most that I control. We have there the rules, like it is a motion with a vertical straight path, something like that. We have to a lot of things there. That's one of the subjects of the free fall, the vertical throw. That is the same, but you have to take the thing and throw it vertically, and then it has to fall. But the free fall, it's used drop an object in rest. We saw the free fall applications. We saw to the Aristotle and Galileo's conception of falling objects. That are some conceptions that these two people do. That the Galileo were that in Europe the Aristotle theory of falling objects was declared for the first time in convincing manner by the works of Galileo Galilei. Falling objects, that are some conceptions that these two people do. That the Galileo were that in Europe the Aristotle theory of falling objects was declared for the first time in convincing manner by the works of Galileo Galilei. And the Aristotle's ideas of motion are at first sight reasonable and close to the common sense, although, like we shall see, the intuitions and common sense suffered a great number of attacks in the development of physics. In Aristotle's doctrine, all things are made of four fundamental elements: the fire, the water, the air, and the ground. Aristotle stated that each of the four elements that make Earth are related at each other, and therefore they have approached to join it. And it was only possible to avoid grouping with other similar elements by the action of many forces that opposed to them. The weight of an object is determined by the proportion contained of each element.
In the stage number 4, we saw motion characteristics in 2 dimensions, horizontal motion, and parabolic motions. We have 3 types of motion: motion with constant velocity, motion with constant acceleration in one case, and motion with constant acceleration in the second case. The first one is described for being a straight line with uniform motion. The second one, which is the motion with constant acceleration in the case number 1, has a straight line motion uniformly accelerated. And in the second case, we have a curvilinear motion in 2 dimensions. The 2 classical phenomena studied for this type of motions are horizontal and parabolic motion. In this figure, we can see that in the letter A, a trajectory describing the launch of a ball that falls to the ground. In the letter B, we can see a trajectory that describes a stream of water. And in the letter C, we can see the trajectory of a ball batted by a baseball player. A particular case of this motion that for simplicity we will take first is the horizontal motion, in which an object is launched horizontally from a certain height. When studying the motion of a projectile, the most general case is the one that corresponds to the projectile throw. When an object is launched with a certain inclination, angle, and with a determined velocity. Types of motion in 2 dimensions. Horizontal motion. The horizontal throw is a motion that is characterized by a curved path that an object follows when it is launched with a horizontal direction. It is the result of the combination of 2 independent displacements, one horizontal at a constant velocity, and the other one is vertical, which starts from rest and is under the action of gravity. This is its vertical velocity increases 9 meters per second as the object is descending. Here we can see that the object initial velocity is 0, and with the pass of the time it will decrease and decrease and decrease. Right here we have that the velocity is 8 meters per second and it was constant velocity. The only thing that changed was the time, 1 second, in this point 2 seconds, and in the last one 3 seconds. Also we can see right here, and right here that with the pass of the seconds the object will move some distance. For example, in the first second, here it says the object have traveled 4.9 meters in a free fall motion. If we want to calculate the velocity of the projectile in a determined point of its path, we combine bx and by. To calculate its magnitude, we use the following expression: b to the square is equal to bx to the square plus by to the square. Here we want to know, in this point, what was the velocity of the object. We use this formula to get the result of a question. We can get the direction of the object with this formula. Tangent is equal to by over bx. Parabolic motion. This motion represents the most general problems of projectiles and consists in launching an object in one direction that forms a certain angle with the horizontal, as it is shown in this figure. We can see that all of the points in the parabolic thrown have a straight vector showing where throw is going. For example, here we have this vector that is its direction is to the right because the parabolic throw is going to the right. Here, 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 and here. We have this vector. We have this vector that is pointing to the upward, because the throw is getting higher and higher, is getting ahead, and we have this vector that shows us how the throw is getting formed. Here, this one is the point where the throw will start to decrease. That's why we don't have an upward vector, and we don't have an horizontal vector. This point where the throw has already take form of decreasing, we have an arrow, a vector going down, pointing down, and we still have this vector that shows that the throw is going to right. The throw was thrown to the right side. And that's it for stage 4, motion in 2 directions. We saw these topics. We hope you like it, and thank you.